And we're back. Welcome back and happy Thursday. Today we will continue on with our discussion of the link layer. But before we begin, some administrative bits. Project number 4 concerning the network layer will be due this evening at the usual 11:59 and 59 seconds. Written exam number 2 will be released on the 15th, 12 noon. Will be a 24-hour take-home exam and will be handed in by 12 noon the following day on the 15th. So why don't we continue? When we last left off, we talked about cyclic redundancy check. And the cyclic redundancy check was a method for checking if there was corruption, bit errors, within a sequence of bits encoded as D many bits for some number field called D. And this was done by creating a code in the receiver by some algorithm, and that code has a relationship based on division with that particular number sequence that is checked for errors. And so let's take a look at multiple access protocols. And so multiple access links, things like wireless, as well as twisted pair copper wire. There are two types of links, so-called point-to-point, which was used way back when for dial-up access, as well as between an Ethernet switch and some host. Now, these things are broadcast-based. They're shared, wire, or some other medium, like the wireless airwaves. And so old-fashioned Ethernet was broadcast-based, upstream hybrid fiber coax for sending data from the home to the internet was broadcast-based, and 802.11 IEEE standard, which is wireless local area networking, is also broadcast-based. And so what does broadcast-based mean? It means that everyone is shouting, so to speak, at the same time in order for their message to make it to some destination. And it's kind of like a group of people at a party. Everyone's trying to talk at the same time. And so you need a protocol then to arbitrate as to which particular host will gain access to the medium at any given point in time if they're all trying to talk at the same time over this medium. So you have a single shared broadcast channel, and you have two or more entities or hosts that simultaneously want to transmit. And so when this happens, they're both propagating energy into the shared medium, and you get what's called a collision, because two nodes are sending and therefore receiving two or more signals at the same time. And so what this multiple access protocol does is it implements a distributed algorithm, and it's the responsibility of this distributed algorithm to determine specifically when a node can transmit and when a node cannot transmit. And so this deals with effectively the channel sharing. But the challenge here is that in order to determine when someone can use the channel, it has to use the channel to do that coordination, because that's the only means for communicating is this shared channel. And so an ideal way to do this is, suppose you have a broadcast channel that has a certain rate, transmission rate. You want to know that when one node wants to transmit, it can send at that rate for the available bandwidth for that channel. And you also want to know when M nodes want to transmit, they get a fractional portion of that transmission rate R. Each one gets its portion, R, divided by M. Moreover, the access protocol needs to be decentralized. There shouldn't be a single coordinator because it's shared. One node could go up and down, and when you have a single coordinator, that provides a bottleneck, which is not a good implementation, does not scale. Moreover, you don't want to have any synchronization of clocks or slots going on. And it should be simple, because simple things can be made to run very, very fast. And so we have media access control protocols, and they come in three major flavors. One is so-called channel partitioning, where you're taking all of the bandwidth available for your shared medium, you're dividing it into a number of pieces based on time, frequency, etc., and then allocating each piece or that part of your channel's bandwidth for the usage of a particular node. You have random access. The channel is not divided, but it allows collisions. And whenever you detect a collision, you recover from it. And if you coordinate or randomize, it's very rare that two hosts are going to use the channel at the same time if they're accessing it randomly, and the sharing is achieved through just how randomization works. There's turn taking. Now in turn taking, the nodes take turns, but nodes that have more to send can take a longer turn or more time for their turn. All right, so let's take a look at channel partitioning. Time division multiple access. Now with time division, access to the channel is chopped up into a bunch of time periods, delta t, called rounds, and each station or node that wants to communicate gets a fixed length slot. Now during this time, you can transmit a packet, and only during this slot, and it's not until your slot comes around again, that you can send another packet. And so imagine then if you had 6 stations or hosts in a local area network in a LAN labeled 1 through 6, and let's say nodes 1, 3, and 4 have packets to send. So if you look at this diagram, well, time increases going to the right, and you can see that time is divided up into delta t's. There are many of them. So that means that first slot, station 1 is going to use. That third slot, station 3 is going to use. That fourth slot, station 4 is going to use. But those unused slots are going to remain idle. That means unused bandwidth because nothing is being sent during those periods of time pertaining to slots 2, 5, and 6. Then there's also frequency division multiple access. With frequency division, the entire frequency spectrum is divided into bands, kind of like channels for radio or TV. And each station or host that wants to communicate is assigned a channel or a frequency band. Now, of course, any unused frequency bands are going to go idle. But in the case of this frequency division multiplexing, you have, for example, 6 frequency bands. And let's say station 1, 3, and 4 are using their frequency bands, but 2, 5, and 6 are not. Those unused channels go idle. And so that's sort of a waste, but the good news is that each station knows that it can communicate at whatever rate that frequency band will support. Then you also have random access. And for random access, when some node or host has a packet that it wishes to send, it tries to transmit at full data rate, assumes it has exclusive usage of the shared medium, and there's no coordination ahead of time among the nodes. So what does this mean? It means 2 nodes can transmit at the same time. And when 2 nodes transmit at the same time, there's more than 1 node's worth of signal energy within that shared medium. So they can certainly detect when someone else is also trying to send data across the shared medium. And when more than one is trying to send, that's called a collision. And so what a random access media access protocol does, it specifies 2 things: how to detect this collision when multiple hosts are trying to send, and how to recover from a collision. Now, this typically means you're going to delay your retransmission, and if you delay some random amount of time, it's very unlikely that you're going to resend at the same time. And that's how this sharing is achieved for random access. And so some examples of random access MAC protocols are slotted Aloha, and we won't talk about those really. CSMA, carrier sense multiple access. CSMA CD, the CD stands for collision detect, and CA stands for collision avoidance. So we won't talk about slotted Aloha, but we will talk about carrier sense multiple access. And what the CSMA does is that you listen before you transmit. You listen on the shared medium to see if anyone else is transmitting. And if you sense someone's transmitting, you stay idle. You don't send your data. But the moment you sense that there's no one else transmitting, you go ahead and you start to transmit. So if the channel seems busy, you defer. And so the analogy in human terms is that you don't want to interrupt someone who's already having an ongoing conversation. It's polite. But collisions can still occur. You can have the propagation of your signal to different nodes won't be received until well after they both start communicating. And so a collision means that an entire packet transmission was wasted. You have distance and you have propagation delay before you can sense if someone else's signal energy is actually in the shared medium. So here in this picture, and this is in the book, we have time going downward direction. At time t0, let's say we have one host that starts to transmit its signal energy in a shared medium. You could assume it's wireless, that's fine. And then at some other time, t1, another host transmits. Now at the point time t1, when that second host started transmitting its signal energy into the shared communication medium, the energy from that first host at time t0 hasn't yet made its way to that second host at time t1. So it's absolutely reasonable for the hardware on that second host at time t1 to sense the channel and say, oh, no one's communicating. Let me go ahead and start putting my packet out into the shared medium. So now they start to overlap. That's where the collision occurs. And there's more signal energy in the shared medium than can be generated by a single host. So now that signal energy makes its way all the way across the space, and then the first host is detecting that signal energy from it and the second host, and the second host is detecting that signal energy from it and the first host. So now that they detect those collisions, the first thing that happens is that first host says, hey, wait a minute, there's more signal energy than from just me. There's a collision here. Let me stop sending. So once it stops sending, now the only signal that exists in that shared medium is from the second host. The second host also says, oh, I've detected that there's more signal energy than from just me. I detected a collision. Let me stop sending. And now they're both backing off from their send. And so with carrier sense multiple access collision detect, well, this collision is detected within a short amount of time, and colliding transmissions are then halted or aborted, and that reduces the wasting of that channel's ability to propagate signals. You're not wasting the bandwidth as much. And so collision detection can be easy in a wired network. You just measure the signal strength on the wire and compare what you transmitted to what you are receiving. Now, this is a lot more difficult in wireless LANs because you can overwhelm your received electromagnetic energy in the environment with your send electromagnetic energy. Plus, you also get reflections and other noise in the environment. And so what the CSMA CD collision detect does, it's a human analogy is a polite conversationalist. You start talking, and then, oops, I'm bumping into somebody. My conversation is interacting with someone else's. Let me go ahead and let me stop or back off. And so here we have our detection of collision, where we have more signal energy in the environment than is responsible from each one of the nodes. And once we detect it, they go ahead and they abort their send to save the available bandwidth available in this shared communication medium. And so what happens in Ethernet, carrier sense multiple access collision detection algorithm? The network interface card receives a datagram from the network layer, creates a frame, and then it starts sensing the channel. If it sees that it's idle, it starts transmitting its frame. But if it senses the channel is busy, it waits for that channel to become idle. Now, if the interface card transmits the whole frame and does not detect another transmission, then it's done. That frame is now transmitted. But if while transmitting it detects another one, it goes ahead, aborts, and sends something called a jam signal. It fills the airwaves with energy to try to encourage other cards to abort as well. After aborting, it then enters a back-off period. Depending on the number of collisions it has counted, it chooses some random number between 0 and 2 to the m minus 1. And then once it chooses that number, it weights that number times 512 bit times. And so it's randomly selecting some amount of time to start that process again, to start communicating. And if that range of numbers is big enough, it's very, very unlikely that two Ethernet cards, network interfaces, are going to wait the same amount of time. In essence, they're choosing slots in time at which to retransmit. And so these intervals that they wait to back off before they resend or try this step one again is going to be longer, therefore lessening the likelihood that it's going to have another collision. The more it collides, the less likely it becomes it's going to have another collision. All right. And so another approach from the access control for having these network interface cards control or coordinate their access to the shared medium is so-called channel partitioning. Now, of course, you want to share the channel efficiently so that you can send a lot of data down it. Now, it's inefficient at low load, much more efficient if you're sending a lot of data by dividing up the bandwidth of the channel explicitly. Now, of course, you have delay in channel access, because if you only have one node active and you're dividing up into n slots or channels, you're only using 1 over n and not as much bandwidth as is available. The random access protocols are efficient if you have low load, because a single node, if there's no collision, no one else transmitting over the shared medium, it can take the entire bandwidth available in that channel, R bits per second. Now, this other one, turn-taking protocols, tries to implement the best of both worlds. So let's take a look at turn-taking. So here, with polling, we have a controller, I'll call it. I'm not going to use the terminology. And we have subordinate nodes. And this controller invites the subordinate nodes to transmit on the network. And this is typically used with very simple subordinate devices. But the problem then that you're concerned with is the overhead of doing this invitation, this polling, and also the latency or delay associated with getting from this polling to the actual sending of data. And so here the controller sends the poll to each node. If you have data, you send it back. And then you send the poll to the next node. If you have data, you send it back in a coordinated fashion. Another one is called token ring. And what happens in this token ring, you arrange your nodes in a ring, circle, on your shared medium. And then you have a special message called a token. And this token is passed to each node around the ring. And if you have data to send, you grab the token, it's your usage of the network, and then you send your data. And that's how they coordinate, by passing this token around the network. And whichever node has the token is the one that can communicate. So here we have the token. If you have data, nothing to send, the token gets sent to the next node. If you have data to send, you now send your data around the ring, the receiver gets it, and then you send the token along the ring so that the next node has the token and can send and receive. But this has some issues with latency, because it takes a while for this token to get around the network. So let's take a look at our hybrid fiber coax setup. And here we have the cable modem termination system. Those are those green boxes you see around most housing or many newer housing communities. And you have your ISP feeding into it, fiber, and then you have coaxial going off into the neighborhood, serving about 500 to 1,000 homes. And so inside the house, you have a splitter that goes off to your TV and your cable modem. And let's recall that cable modem was originally intended for television and pay-per-view. And so the downstream speeds were typically faster than the upstream speeds. Now here we have our internet frames, TV channels, and control transmitted downstream at different frequencies. TV lends itself to different frequencies. And upstream, you have internet frames. TV control messages are transmitted at different frequencies, but also in different time slots. And so you have multiple 40 megabit per second downstream channels, and you have a single CMTS, cable modem termination system, transmitting into these channels. So you have all that traffic, which is TV, in addition to the internet traffic going downstream, and then you also have multiple 30 megabit per second upstream channels. Now, of course, these upstream channels are multiple access. You have all of the users on your local trunk for your cable modem network, the coaxial side. They're all contending for slots in time to use to send data upstream. So if you ever notice for cable modem, During peak times, let's say right after dinner time or in the early evening, you'll notice it slows down. And in the advertising for cable modem products, they'll always say up to 200 megabits per second. Now that up to is going to vary. Your mileage will vary depending on how much contention you have for those upstream time slots. And so here, DOCSIS, Data over Cable Service Interface Spec, is primary means that they use for signaling for cable modems to get data upstream and downstream. Now, DOCSIS implements frequency division multiplexing, the division of your shared medium's bandwidth into channels or frequencies over upstream, and also downstream has frequency channels as well. Now, of course, the time division multiplexing part for the upstream portion has some time-based slots pre-assigned, and some have contention. Now, in the downstream, there's a frame that is sent that can be used for the assignment of upstream slots for the upstream direction. And so you can effectively, as a household on the cable access network, you can request upstream slots that can be granted to you, assigned to you, and then you can transmit up. You can also do random access with a binary backoff for these slots. So it does kind of a hybrid. There's random access with binary backoff, but there's also reservation of slots as well. Okay, and so summarizing media access protocols, we have partitioning by time, frequency, or slotted. We also have random access. We have carrier sensing. It's easier in wired than it is in wireless. There's collision detection. Carrier sense multiple access collision detect is what's used in Ethernet, and carrier sense multiple access collision avoidance is what's used in Wi-Fi, wireless Ethernet, IEEE standard 802.11. And then there's also turn taking. That's polling from a central site, which does polling with the subordinate and the controller, or token passing. Now, turn taking, Bluetooth does turn taking, a standard called FDDI, and an old networking standard called token ring. There used to be something back in the 90s, early 90s, called token ring networks. All right. So let's take a look at the addressing for network interface cards in the link layer. And we said that the link layer is purposed with sending frames between nodes that share the same communication. So let's say that we have our setup here. We have two hosts, A on the left, and we have B on the right. Now, one of the things you'll notice that there's an IP address. We have our dotted quads. For example, host A it has 111.111.111.111. We also have this other number, and this number consists of 2, 4, 6, 8, 10, 12 hexadecimal digits. Each hexadecimal digit corresponds to 4 bits. So we have 8, 16, 24, a total of 48 bits for the MAC address. Now, MAC address stands for Media Access Control Address. And the MAC address is unique for the network interface card, and it identifies that network interface card to all other nodes on the same communication medium, on the same network. Now, of course, what happens is, let's say you want to forward a datagram that has a source of IP address for A and a destination for IP address B. Now, of course, that should be an A, that's a typo. You're going to create from that datagram a link layer frame, and it's going to have two things. It's going to have B's destination IP address if it's sourced in host A, and it's going to have B's MAC address. And so what happens then when this frame gets to the router? Well, this router, it has two interfaces. One interface it shares with the network for host A, and the other interface it shares with the network that's reachable to host B. And so here, when we get to this router, we send to the MAC address for this router, and then when the router gets this datagram, it changes the source MAC address and the destination MAC address when it forwards that datagram from the source network to the destination network. And so here, our router is going to create a link layer frame, and it's going to contain B's MAC address, which is going to be 49 BD D2 C7 562A, and that's going to be the destination MAC address. And the source MAC address is going to be changed from the source MAC address of host A to the source MAC address of that interface for that router that it shares with that network for IP address for host B. And so now we see that this router then, when it takes that frame off the network, it sends it to its link layer, it strips out that datagram, sends it to the network layer, it looks up the forwarding address for that destination IP, for the IP address for B, and then it sends that datagram back down into the link layer where it rewrites the source and the destination MAC address once it knows the output port, because the output port has a different MAC address. And so now it takes that frame, pushes it out onto its physical layer, it gets transmitted onto that shared medium that's shared with B. B sees the destination MAC address matches its own, so it takes that frame, pulls it up into its physical layer, strips out that datagram, sends it to its IP layer, and then it delivers that to the transport layer, which then gets it to the application layer, and that frame is now sent. And so this MAC address identifies each host on the same network. MAC addresses only live on a network. IP addresses are global and live across networks. And the router knows which port to forward that datagram out of, rewrites the source and destination MAC address so that it can then get that frame ultimately to the link layer of that host on the same network that is shared with the output port of the router. Okay, so now that we have this frame in our destination host, it strips out that datagram stored inside of the link layer frame, and it's then delivered. So with that, we will end there. And as usual, please stay healthy, stay safe, and I'll see you all on Tuesday.